All right, let's talk about something that's happening all around us and inside of us, literally every second of the day. Acids and bases. It's this invisible chemistry that's constantly keeping our world and our bodies in perfect balance.
So, let's start with a kind of weird question. What on earth do lemons, soap, and your own blood have in common? I mean, they seem totally unrelated, right? Well, the answer is that they all play a part in this world of acids and bases.
To really get what's going on, we got to shrink down to the molecular level. We need to look at the one tiny particle that runs this whole show, the proton. You can think of it all as a constant chemical exchange, kind of like a proton dance.
You know, it all really boils down to this super simple game of give and take. It's called the Brønsted Lowry theory, and it just says this: an acid is anything that donates a proton, and that proton is just a hydrogen ion, that H+. So a base? Well, a base is simply the thing that accepts that proton. That's it. That's the fundamental rule of the dance.
So think of it this way. In this dance, you've got two main roles. You've got the acid, which is the generous giver, it's handing off its proton. And then you have the base, the taker, which is ready to accept it. You really can't have one without the other.
Okay, so let's watch this happen in real time. Picture this. Ammonia, which is a common base, bumps into a water molecule. Now in this scenario, water actually plays the role of the acid. It donates one of its protons straight to the ammonia. The ammonia grabs it, and poof, they both transform into totally new things, ammonium and hydroxide. See? The proton just switched partners.
Okay, so if this is all about donating and accepting protons, how do we actually measure it? How do we keep score of how acidic or basic something is? Well, that's where the pH scale comes in. It's basically the power meter for this whole process.
So, what exactly is pH? It's really just a way to measure the concentration of those hydrogen ions we've been talking about, and that little p actually stands for power. Now, the formula might look a little scary, but the key thing to know is that it's a logarithmic scale. That means every single number you go down isn't just one step, it's a 10 times jump in acidity. So a pH of 3 is way more acidic than a pH of 4.
And right smack in the middle of this entire scale is the magic number 7. A pH of exactly 7 is perfectly neutral. It's the balance point. Think of pure water. It's not an acid, it's not a base. It's kind of like the Switzerland of chemistry.
So, starting from that perfect middle point of 7, the scale splits in two directions. Anything with a pH below 7 is acidic, and the lower the number, the stronger the acid. Then anything above 7 is basic or alkaline, and its strength goes up the higher the number gets.
Okay, but here's where it gets really interesting. It's not just about whether something is an acid or not. We also need to know how it behaves when you put it in water. Does it go all in, or does it kind of hold back? So are all acids basically the same? Nope. Not even close. There is a massive difference between, say, the acid in a car battery and the citric acid in your orange juice, and it all comes down to one thing: strength.
And that difference? It really just comes down to commitment. A strong acid is the all-in type. The second it hits water, pretty much every single molecule gives up its proton. It just completely falls apart, or dissociates. But a weak acid, it holds back. Only some of its molecules actually donate a proton, which creates this nice little balance in the water.
You know, what's kind of funny is that the strong acid club is super exclusive. There are only a handful of common ones you really need to know, and these are the big ones right here. Here's a helpful tip. If you see an acid and it's not on this short list, you can be pretty sure it's a weak one.
All right, so we've got these intense, all-in acids and the more chill, holding back ones. But what if you need things to stay, well, stable? What if you can't have the pH swinging all over the place? Well, nature has this incredibly cool solution, and it's called a buffer. This is where we see the chemistry of keeping things in balance.
Think of a buffer as a pH bodyguard. Seriously, it's a special kind of solution that can take a hit from an incoming acid or a base, and the overall pH barely even flinches. And the secret to its power is its two-person team, a weak acid working together with its conjugate base, which is really just a fancy name for what's left over after that weak acid donates its proton.
So how does this bodyguard actually do its job? Well, it's got this amazing two-part system ready to go. If some outside acid comes along and tries to drop the pH, the base part of the buffer jumps in and neutralizes it. And if some outside base tries to raise the pH, the acid part of the buffer takes care of business. It's this perfect two-way defense that just holds everything steady.
All right, let's do a super quick recap of the big ideas we've covered. We started with the Brønsted Lowry theory. Acids are proton donors, bases are proton acceptors. Simple. We learned the pH scale measures all this, with 7 being that perfect neutral spot. Then we saw that strong acids go all in and completely dissociate, while weak acids don't. And finally, we talked about buffers, those amazing solutions that use a weak acid and its partner base to keep pH from changing.
And that brings us to one last really important thought. It's about you. Your blood is an incredibly complex buffer system. It works nonstop to hold your body's pH at a very precise 7.4. Literally every biological process you have depends on that number staying stable. So what would happen if that buffer system just failed? It's a pretty intense question, but it shows you just how critical this chemistry of balance is for life itself. Something to think about.